Good afternoon all. May I remind all the registered participants that you must mute your mic. Questions may be typed at the end of the session. We begin with session 2 of the workshop. This session is chaired by Dr. Seethu Varghese and the speaker is Professor A. Vijay Kumar. Now I request Dr. Seethu Varghese to chair the session.
Good afternoon, everyone. I am very happy to introduce my guru, Professor Vijay Kumar sir, to handle the session. Professor Vijay Kumar is a native of Palakkad district. After his graduation from Government College Chittoor, he did MSc and PhD from Cochin University of Science and Technology way back in 1980s. He started his career at REC Calicut and worked there for 2 years. Then he joined Department of Mathematics CUSAT and continued there till 2018 when he officially retired from service. He is still continuing in the same department as Emeritus Professor. He is a member of various organizations like Indian Mathematical Society, Academy of Discrete Mathematics and its Applications, Ramanujan Mathematical Society, Cryptology Research Society of India, American Mathematical Society, Canadian Mathematical Society, etc. He is a fellow of Institute of Combinatorics and Applications Canada. He is the vice president of Ramanujan Mathematical Society. He's an enthusiastic traveler and has visited and given talks in many foreign institutions like Hungary, Canada, Taiwan, South Korea, Mexico, Czech Republic, Spain, and Italy. He has also delivered talks in various institutions in India like ISI, Calcutta, University of Hyderabad, and many more. He's a real math educator and is very active in the field of popularization of mathematics. He was the regional coordinator of Mathematical Olympiad from 1990 to 2017. He also does consultancy for Malayalam translation at Kerala Language Institute. He was involved in translating the book Man Who Knew Infinity. He gives popular lectures and writes popular articles both in Malayalam and in English. He is a mentor for the INSPIRE program by Department of Science and Technology. He had the pleasure and honor of meeting our former president, APJ Abdul Kalam, and he had interactions with him. Vijay Kumar sir has a habit of asking questions and he always encourages students to ask questions. Some of these questions were easy, others complicated, some others tricky. But most of them had a happy ending in the form of 14 PhD theses. And all of his students are still continuing this habit and doing a wonderful job in graph theory. Research group at CUSAT under his guidance is working on various topics of graph theory like graph operators, spectral graph theory, graph dominations, etc. And he has 80 publications to his credit. And I was really blessed to have him as my guide. And he is indeed a friend, philosopher, and guide to all of us. With these words, I invite Professor Vijay Kumar sir to this session. Sir, please.
Okay, thank you. Good afternoon. So afternoon timings is not fit for mathematics actually. But I think you are given enough timing gap so that you could have lunch and then have a nap and then come to this program fresh. So I will try to share, but it says that you are not allowed to share. I don't know what is happening.
Just a minute.
Yeah, so
Please check now.
it's okay. Is it okay?
Yes, sir.
Yes.
Yeah. Yes, sir.
Okay, fine. I'm going to talk on generalized power domination. I understand that most of the participants are get into the real problems of doing research. So I will go slow and try to make you understand whatever things that I am going to discuss here. So before talking about generalized power domination, I need to talk about power domination. Before power domination, I should talk at least 1 or 2 lines about domination, which has been already dominated by Professor Armugam in the morning. So domination problem came out of, in fact, almost all problems of graph theory. That's the uniqueness of the subject. Almost all branches of graph theory came out of solving simple looking puzzles. I mean simple looking, not necessarily simple. Simple looking puzzles like Konigsberg Bridge problem, around the world problem called Icosian games, and so many, say for example, storage problem, timetabling problem, all party problem, and so on. So all these puzzles turned out to be leading to some theorems, and that is how the graph theory grew from 1736 to as is on 2021. Those who are new to this subject, I strongly refer a book by name, Graph Theory 1736-1936 by Biggs, Lloyd, and Wilson. 1736 is the origin of graph theory by Euler, and 1936 is the year where the first book on graph theory by Koenig came, Theory of Graphs, Finite and Infinite Graphs in German language. So if one plans to write a book on graph theory from 1936 to 2020, the earlier book had 3 authors, and even if we have some 10 authors, we are almost sure that we will not be able to complete the book, exhaustively complete the book, because from 1936 to 2020, graph theory has grown like anything. In between, in 1950s, computer science came, so that added to the growth, and we are now in the field of computational biology, brain networks, epidemiological networks, and so on, what is called the graph theory in the information age. So this 14-member group is my asset. Whatever I did after my PhD way back in 1985, the credit goes to this 14 group battalion. And of course, I am the dominating vertex. All the 14 members are adjacent to me. They themselves have formed cliques, subgroups, and all these things. So I am proud to be the leader of this group. And as per UGC guidelines, I cannot encourage these 14, but always collaborations are welcome. I can branch at any point of that 14 member. I can start with either Manju or Savida. You see that Savida and Manju are faculty members of St. Paul's College organizer. And the 3 speakers of today, of this workshop, Sidhu Varghese, Tijo, and one more, Chitra. Yeah, they are also my students. I am proud of them. They are smarter than what I am. So any questions after my talk, I will take the question, but the answers will be given by my students, just like Albert Einstein did once. Okay. So this is the basic agenda. Various problems under discussion will be like domination problem. You should know what it is and how this problem was motivated. Gamma graph, and then bondage number. Then I will go to the power domination problem, basic results, and I need to generalize power domination to discuss the notion of bondage in power domination. That is the rough plan. I'm not in a hurry, and I don't have any fixed destination. Whenever I feel like stopping, or whenever I am working on a speed, please restrict me. I will be happy to help you. Okay. So as mentioned in the morning by Professor Armugam, who is one of the leading domination experts in the country, this problem was discussed in a different way, but it's a famous problem of chessboards. That we have a chessboard, standard chessboard is 8x8 chessboard, but we can ask questions for any n by n chessboard. So for example, you can ask which n by n chessboard admits a knight tour in the chessboard. Okay, you know the movement of the knight, K-N-I-G-H-T. So you can ask which n by n chessboard admits a knight's tour. Is an associated problem coming from the chessboard. So here we have about what's called the queen's domination, a problem which came as a chessboard problem in 19th century. Determine the minimum number of queens that could be placed, such that each square that was not occupied by one of the queens was attacked by at least one queen. Now, I strongly refer to the book by Watkins, Across the Board, Across the Chessboard, actually, Princeton University Press 2004. There are plenty of open problems there, and I feel that we can get at least some 10 to 15 PhDs. So this problem is now called queen's domination problem. Okay, so this is one of the popular solutions of the queen's domination problem. If you put the queens in the red spot, you can see that the rule is followed, and therefore in an 8-by chessboard, the minimum number of queens required is 5, and therefore the queen's domination number for an 8-by chessboard is 5. But what is surprising is that's where the combinatorics shows its strength. As per the book, there are more than 4,860 possible solutions for the queen's domination problem. So that is something interesting. Suppose you have another examples. For example, I have done here 1 1 3 3 5 5 6 6 7 7. It could be 3 6 4 3 5 5 6 7 and 7 4. I shall repeat. One other solution is 3 6 4 3 5 5 6 7 and 7 4. So like that, there are more than different solutions. I mean, solutions which is not obtained by permuting these rows and columns. Totally different solutions. There are more than 4,800 possible solutions. So this is one of the motivation for defining the notion of domination in the graph theory. So if you denote by NGV the set of vertices adjacent to V, that means the number of vertices, the degree of the particular vertex V. And if you take NGV to be, you adjoin NGV union V, that is what's called the closed neighborhood. And union of all such closed neighborhood for all possible S contained in VG, subset of vertex set of G, is NG closed S. So you have been hearing about the definition of dominating set. Just for completion, I am taking that a subset of vertices is a dominating set if each vertex of G that is not in S is adjacent to at least one vertex of S. A dominating set of minimum cardinality in G is called a minimum dominating set, what is called gamma set. So gamma set is a subset where is a dominating set containing gamma with gamma vertices, and its cardinality is what's called the domination number. So if you take this graph, you know gamma G is 3 because if you take the blue vertices are satisfying the property. Therefore, and I cannot do it with less than 3. Therefore, the domination number of this graph is 3. It is the minimum. Okay. From this notion of gamma set, there is a notion of gamma graph of a graph. Namely, suppose you look at the collection of all gamma sets in a graph G. That is, collection of all subsets of vertices whose cardinality is the domination number. Then the gamma graph of G, denoted by gamma dot G, is the graph with the vertex set D. And any two vertices D1 and D2 are adjacent if the cardinality of D1 intersection D2 is gamma G minus 1. And a graph is called a gamma graph if there exists a graph G such that H is equal to gamma dot G. It is a paper by Professor Sridharan and Subramanian. And we have some interesting research based on that, which are yet to discuss. So G is connected need not imply that the gamma graph is connected and vice versa, because gamma graph of 2K2 is C4 and gamma graph of C6 is 3 times K1. Complete graphs are gamma graphs. Gamma graphs of parts cycles are studied in a paper by Sridharan, and It's proved that trees unicyclic graphs are gamma graphs. From a paper in 2010 by one of my students, Aparna, is that we define the join of two graphs as a graph which vertex set of G1 union vertex set of G2 and edge set of G1 union edge set of G2 union set of all edges joining a vertex of G1 with a vertex of G2. So all edges of G1 are there, all edges of G2 are also there. In addition, there are edges which are joining vertices of G1 with vertices of G2. That is precisely G1 join G2. And H is a gamma graph, then H does not contain K3 2, T3 join K2, K2 union K1 join 2 times K1 as an induced subgraph. So there is a forbidden subgraph characterization of gamma graph. Okay. So for more information, I can refer to the papers by Aparna. And also there are some other notions of gamma graph which is discussed in literature. You please refer from the Google. Okay, so now we'll go to the notion of a bondage number. This happens when I need to measure the vulnerability of the interconnection network under failure. What is going to happen to the network when particular edge gets deleted or particular vertex gets deleted? That is altogether there in many branches of graph theory. What is happening for example, spectral graph theory or graph energy? If you remove one vertex or remove one edge, what is happening to the energy? Or many other topics like chromatic number. Also, we are interested in chromatic number of G minus V, chromatic number of G minus E that may change or may not change like that. So Fink in 1990, in his celebrated paper which appeared in discrete maths called the bondage number of a graph, introduced the concept of bondage number as a parameter to measure the vulnerability of the interconnection network under failure. So the bondage number of a connected graph G is the minimum cardinality among all sets of edges B of G, for which when you remove those edges B number of edges, its domination number increases. Gamma G minus B is greater than gamma of G if I remove. So, and B is the minimum number of edges whose removal makes this increase the domination number. So BG, what's called the bondage number, is precisely minimum of B, cardinality of B. B is subset of BG such that gamma of G minus B, if I remove B number of edges and not less than that, the gamma, the domination number increases. So exact values of the bondage number is known for some classes of graphs, and sharp upper bounds for BG are obtained in a paper by Hartnell in 1994. Douglas Rahl is one of the speakers of this workshop. Douglas Rahl and Hartnell did it in 1994 for obtaining some bounds and all that. And the survey, those who want to start working on bondage number and related topic, I will strongly recommend the survey paper by Xu, which is roughly a long paper, 30 pages or so. Okay, which came in International Journal of Combinatorics. And if you take this graph, you can easily see that. So these are the homeworks which you could do. Gamma G is 2. Obviously, these blue vertices dominates all other vertices, and you can see that its bondage number is 2, and 2 is the minimum number of edges whose removal increases its bondage number. Domination number. It's known about some classes of graphs. Bondage number of Kn is n by 2 ceiling, and the bondage number of a path is 2 or 3 according as my n is 1, n is congruent to 1 mod 3, and or otherwise, and bondage number of Cn, cycle of length n is 3, n is congruent to 1 mod 3, and Bcn is equal to 2 otherwise. Now, trees are always specimens for any discussion on graph theory, so we will first try to get results on trees. So for any non-trivial tree, it's known that the bondage number is at most 2, and in a paper by Xu, a survey with some comments on bondage numbers, 2013, it says that they are characterized trees with the bondage number 1 or 2. G is a non-empty graph with unique minimum dominating set. In fact, this was put under discussion when I presented this last time somewhere in Delhi. So graphs with unique minimum dominating set is a particular class, and there is a good paper by Douglas Rall on those who are interested. We can send you on graphs with unique minimum dominating set, and for such graphs, bondage number is 1. And if any vertex of a graph G is adjacent to 2 or more vertices of degree 1, then also we can see that bondage number is 1. So we have some bounds for bondage number of trees, but we have some results on in the literature with the graphs 1, bondage number 1. And as usual, we try to, if we cannot get the exact value, this is what is happening in general graph theory in many other branches also. If G is a connected graph, then I can bound it with lambda G plus delta G minus 1. So BG cannot exceed lambda G. Lambda G is the vertex, edge connectivity, and delta G is the maximum degree. Edge connectivity is minimum number of edges whose removal disconnects the graph if you start with a connected graph. Okay, so lambda G, for beginners I am telling it repeatedly, lambda G is the minimum number of edges whose removal disconnects the graph. This is what is called the edge connectivity, and delta G is the maximum degree of the graph. And there is a theorem by Hartnell and Rall again that G is a connected graph, then the bondage number is bounded by lambda G plus delta G minus 1. And the bound is attained for a cycle of length 3k plus 1. And we can see that the bondage number is 3. These are all simple calculations that you can do. And kappa C3k plus 1 is definitely a cycle. Therefore, its vertex connectivity is 1. And it's also edge connectivity is also, vertex connectivity coincides with edge connectivity because it's going to be a 3 regular graph. Yes. Therefore, it is 2, and maximum degree is of any cycle is 2, and therefore lambda C3k plus 1 plus delta of C3k plus 1 minus all these conditions are satisfied, and therefore it's an example where the bondage number is equal to lambda G plus delta G minus 1. And there was a conjecture because there is a relationship between kappa G and delta G, kappa G and delta G and lambda G by what is called the Whitney's theorem, which says that for any connected graph G, kappa G is less than or equal to lambda G is less than or equal to delta G. That is, vertex connectivity is less than or equal to edge connectivity, and both of them cannot exceed the maximum degree of the vertex. So motivated by that, there came a conjecture that by Liu solved it in 17, which came in 1998, and this conjecture was disproved in 5 years by Liu and Sun, bondage and connectivity of a graph, which came in discrete mathematics 2003. They gave a counterexample. So the conjecture is disproved. So you take the disjoint union of 2 copies of H. H is this graph by identifying 2 vertices of degree 2. So this is a vertex of degree 2, and you take another copy of the same graph and what we call fuse it here at this vertex. So the graph becomes a 4 regular graph, and its kappa vertex connectivity is 1, and edge connectivity, maximum degree is 4, and edge connectivity is 2, and so BG is less than or equal to lambda G plus delta G minus 1. So this fails, and this is BG is 5, and 5 is greater than delta G plus KG minus 1. So they gave a counterexample to the conjecture of in 31. Okay, there are some more bounds for bondage number. For a connected graph G, BG is less than or equal to n minus 1. BG is less than or equal to delta G plus 1 if gamma G is equal to 2, and BG is less than or equal to n minus gamma G plus 1, and all the 3 bounds are attained for the complete T-parted graph KT2. Okay. So these are the things which I wanted to tell in the first 3 points, that is domination, gamma graph and bondage. Some we have results on bondage notions in the power domination, which we will discuss. Now let us tell me the story behind this notion of power domination. So motivation for power domination comes from electrical power networks. And you know, an electrical power network contains a set of nodes, what are called buses, and a set of edges connecting these nodes. That's the basic electrical connection network. So a power network also contains a set of generators which supply power and set of loads where the power is directed. In order to optimize the power network, in order to monitor a power network, we have to measure all state variables of the network by placing the so-called phase measurement unit. And a phase measurement unit is a device placed on a vertex that has the ability to measure the voltage of the vertex and the current phase of the edges connected to the nodes. We need to optimize the number of phase measurement units used. So because PMs are expensive, so it becomes a minimization problem. So the goal is to install the minimum number of PMUs such that the whole system is can be monitored. This came as a problem as early as 1993, and it was modeled as a graph theory problem by Haynes, Herednimi, and Hennings in 2002. So obviously, when you are dealing with electrical power networks, two fundamental laws of physics, namely the Ohm's law and Kirchhoff's law, should play a role. And finally, this was all settled, and that was converted into solely as a problem of vertices by two papers in 2005 and 6 by Brunei et al. And Dorfling and Henning in discrete applied mathematics. So basically now, the domination problem is basically a problem on the vertex set of the associated graph. So the power domination problem, PDP, is to find the minimum number of PMUs needed to monitor a given electrical power system. So we have certain rules to follow, just like we have a rule of domination in the case of finding the domination number. So I assume that the graph V is, represents an electrical power system where the vertex represents an electrical node and an edge represents a transmission line joining two electrical nodes. So by domination, there are two steps which are involved: domination step and propagation step. What you do by domination step is a vertex with a PMU monitors its closed neighborhood. That is, all vertices which are neighbor to this vertex, including that vertex, closed neighborhood. By propagation step, if a monitored vertex has a single neighbor not monitored, I will mathematically define this in the next slide. If a monitored vertex has a single neighbor not monitored, I am including that vertex also along to the already monitored set. Okay, so these propagational rules are derived from Ohm's and Kirchhoff laws I mentioned earlier. Those who are interested in its origin, I can give you the reference. So the power domination number is the minimum number of phase measurement units that monitors the whole graph, and that is denoted by gamma PG. Okay, so we'll make it formal. So I have a graph G is equal to VE, which represents the vertex represents an electrical node and an edge represents a transmission line joining two electrical nodes. For a subset S of VG, the set monitored by S. This is a very important point that you have to know when you are trying to find the domination number. So a set S monitored by S, what is called M of S, is recursively defined as follows. So first is dominating step that I am going to adjoin for all vertices of S, its neighbors also. So MS is replaced by S union N of S, neighbors of S. Now, propagation step, the second rule which I mentioned, as long as there is only one vertex which is a neighbor of a vertex which is already in M of S, but not already included in my M of S, I am going to adjoin that also. So I shall repeat that. If NV intersection VG minus MS is W, that is, W is the only vertex which is a neighbor of V, where V is already monitored, but not included in my M of S, I am going to adjoin that also. Okay, So MS becomes MS union W, where W has the property that W is the unique vertex, the only vertex, so that it belongs to neighborhood of V, and it's a vertex set of G, but not already included in my monitoring step. So this is the definition of M of S. Let us try to find M of S. So if M of S fills the entire graph G, and that S with the minimum cardinality is what is called the power domination number. So if you take this, for example, you start with U and V. So by the domination step, it takes care of this vertex, this vertex, this vertex. It is symmetric. The graph is symmetric in some sense. So I'm concentrating only on the left side. So if you take U, this, and this are already in the domination step. Now comes this vector. This is a neighbor of V, and this is the only neighbor of V which is not at already monitored. Okay, so this vertex is the only neighbor of this vertex which is already monitored. Therefore, I am going to include this. Similarly, this is the only vertex which is neighbor of. Now this is the MS. It has increased by 1, and this also has the same property that it is the only vertex which is in a neighbor of this vertex, but not already included in the monitoring set. Therefore, I am going to use this also, and I cannot proceed further by domination rule and propagation rule. Therefore, my M of S consists of all the dark vertices. Okay, and it doesn't fill the entire graph G. Therefore, it's only an example of a monitoring set, and it's not going to be the minimum power dominating set. I just gave this example to show you the definition of monitoring set. Okay, so a set is called a power dominating set, PDS, if M of S is the entire VG, and the power domination number of G is the minimum cardinality of a power dominating set of G. So we have placed the necessary definitions to proceed with. Everything is fine as such, and any points to be clarified, I will be happy to do this at this point. I hope that the definition of power dominating set is okay. Is it all right? Somebody should say yes,
Yes,
or somebody should say no.
Yes, sir.
Pardon?
Yes. Yes, sir.
Okay. Fine. So if you find the great Peterson graph, which is a notorious graph, as far as the youngsters are concerned, there's a whole book devoted to Peterson graph. Very many properties of Peterson graph. It's a very notorious graph, which doesn't satisfy all the known properties, but it's a counterexample, or it's a hero for many concepts in graph theory. Okay, so I'm starting with the two vertices U and V, and I say that the power domination number, or I can fill the entire graph, Peterson graph, by doing the domination step and the monitoring step on these two vertices. At the first level, all the neighbors are taken care of. That is what's called the domination step. So first level, all the neighbors of these two vertices, which are colored with say red or orange, is taken care of. And next step is the propagation rule. This comes into picture because this is the only vertex which is adjacent to this and not included in the already monitoring set. So I'm going to include this. So by symmetry, I'm going to include these three also. So starting with the two vertices U and V, and 2 is the minimum. I can reach through domination and propagation the entire graph, entire Peterson graph. Therefore, by definition, U is the P, U and V are the minimum 2. So the power domination number of Peterson graph is 2. Now this is a graph which is should be a personal graph to all Indians, because those who have not heard me before, newcomers, if I'll be happy if somebody can tell what is this graph, or which is this graph, or what is the name of this graph. Heard me earlier, please don't interfere. Let newcomers say, or I wanted to know whether how far you know about the properties of this graph. This is popularly called Srikhande graph, named after an Indian mathematician, Srikhande, who passed away last year at the age of 102. And he's one of the Euler spoilers. I'm a fan of Srikhande because even at the age of 102, he used to discuss mathematics. That is something people cannot think about. Okay, she's that lucky, that fortunate to have mathematics being discussed at the age of 102. So Srikanday graph is a strongly regular graph. Strongly regular graph means it's basically a regular graph with a regularity 6 vertices. Number of vertices is 16. So by the fundamental handshaking lemma, there are 16 vertices and each vertex is of degree 6. Therefore, it has got 48 edges. So Srikanday graph is a graph 6 regular, 16 vertex, 48 edges
So
graph.
someone has raised a hand. Manjunath has raised his hand. Is Manjunath, do you have any doubt? You can ask the speaker. Manjunath? Manjunath, can you hear me?
Shall we have towards the end of this?
Okay.
Okay. So this is a strongly regular graph. A graph is a strongly regular graph is strongly regular if it has got n vertices, regularity is k, and there are two other parameters, lambda and mu. Lambda gives any pair of non-adjacent vertices have lambda common neighbors, and any pair of adjacent vertices also have mu common neighbors. Then n, k, lambda, mu becomes the parameters of the strongly regular graph. So I shall repeat. If you take any two vertices which are either adjacent or not adjacent, in this graph there are two vertices which is a common neighbor of this. So Srikanday graph is a strongly regular graph. The theory of strongly regular graph is very rich and it's purely Indian. It is R.C. Bose and Srikanday who did lot of results in strongly regular graphs as early as 1960s. And so this Srikanday graph is a graph with 16 vertices, regularity 6. Whether it is any two vertices are either adjacent or not, there are two vertices which are common neighbors of these two. So therefore, Srikanday graph is a graph with parameters 16, 6, 2, 2. And what is so famous about this Srikanday graph is that it is Hamiltonian, because the vertex degree is regularity 6. It's an Eulerian graph. It's a Hamiltonian graph, but it is not a planar graph. It's not a planar graph means I cannot embed this graph in the surface of a sphere and therefore in the plane without crossing of its edges. So if you try to draw the 48th edges, that's a very interesting exercise for beginners. Try to draw this graph such that it can be crossed only at one point, that is crossing number is 1. So we can find this, you can see that I cannot draw this graph without crossing all the edges, that is 48 edges I cannot draw, but 47 I can draw, and if you judiciously do it, it's a simple exercise but takes some time, that's all. We can prove that its crossing number is 1, and it's also toroidal in the sense that I can embed this graph in the surface of a torus following the rules that there is no crossing of edges. So this is an example of a graph which is planar, but not planar, but toroidal, the surface of a torus, that just like cycle tube or vada that you have, we can embed this in the surface of that torus without crossing of edges. So what I wanted to tell you is that this graph is a very interesting object. Its chromatic number is 4, edge chromatic number is 6, something like that. Edge connectivity is 6, and many properties are known. We can also find the power domination number, and we can see that the power domination number of Srikanday graph is 2. These two blue vertices will take care of power domination, and you can easily so that this 2 is minimum. Okay, so for any graph G, the obviously gamma PG is less than or equal to gamma G, because any dominating set is a power dominating set. So this inequality is true. But what is interesting is that for every k, we can find with a fixed k, I can find a graph with the gamma PG is equal to gamma G is equal to k. What you have to do is you take a path on k vertices and take its corona with the k2. That means you have a path, say P1, P2, P3, etc. Sorry, V1, V2, etc. Vn. Each at V1, you put a triangle there. You keep a triangle. Another vertex, you put a triangle. That is what is called PK, corona K2. I suppose the definition is clear. For that graph, you can easily see that gamma Pg is equal to gamma G is equal to K. So given K. And also, this gamma Pg minus gamma G could, gamma G minus gamma Pg could be arbitrarily large. For that, you take a star K1K and make its corona with K1. You can see that its power domination number is 1. And the domination number of that T, which is K1K, corona K1, is K plus 1. So it can be arbitrarily large. So if G belong to the family of graphs, complete graph, cycle, path, and complete bipartite graph K2N, its gamma Pg is equal to 1. And in all further discussions, the spider is going to play a definite role. So spider is a tree formed from a star by subdividing any number of its edges, any number of times. So you take K1N, star any K1N, you divide each edge any number of times. Is what's called a spider. So for any tree, among the class of trees, the power domination number is 1 if and only if T is a spider. So T is a spider means its power domination is 1, and power domination is 1 among the class of trees implies that the tree has to be a spider, something like this. Okay. Again, some results on power domination in trees. A vertex adjacent to a leaf is called a support vertex, and a vertex adjacent to 2 or more leaves is called a strong support vertex. So with this definition of that, for any tree T of order at least 3, power number of T is same as the domination number of T if and only if T has a unique gamma T set S, and every vertex in S is a strong support vertex. So this is a theorem which characterizes those trees with the same power domination number and domination number. This is another interesting parameter which helps in the power domination, finding the power domination number, etc. What is called the spider number. The spider number of a tree T is the minimum number of subsets such that Vt can be partitioned so that each subset induces a spider. So spider number is the minimum number of spiders which will partition the entire vertex set of the graph. And I will give an example later. For any tree T, the power domination number of a tree is same as its spider number. So I will give an example. If you take the left, it's easy to see that its spider number is 3. This violet colored spider and the red colored spider and the green colored spider partitions the whole vertex set of the tree T. Therefore, the spider number of this graph is 3. And what it says, previous theorem says, is that the power domination number is also 3. So these 3 blue vertices is going to power dominate the entire graph, because at the first domination level, this is what is happening. All its neighbors are taken care of, and follow the rule. This is what is happening. Still, we are not able to do it. So at the third step, what we get is that we are able to fill the entire graph. Therefore, by definition, the power domination number is 3, which equals the spider number. So the notion of spider, later on also for our investigations, the notion of spider is very significant because it's going to help. Okay, so another theorem is again a bound on the power domination number. G is a connected graph of order at least 3, and then the power domination number of G is at most n by 3 with equality if and only if G is K33, complete tripartite graph K33, or G is the corona, G dashed corona H2, where G dashed is any connected graph and H2 is in either K2 or K2 complement. So let me read it again. the power domination number cannot exceed n by 3, and power domination number is equal to n by 3 if and only if G is either K33, that can be easily checked. K33, n is 6, so, and for that it is 2. Or the graph G is the corona, G dashed corona H2, where H2 is K2 or K2 complement, and G dashed is, G dashed is any connected graph. So if you take this example, say K3 corona K2, so G dashed is K3. So what it says is that it has got 3 plus 2, 5 plus 2, 7, 4. Okay. So the 9 by 3, it is 3. So the power domination number is 3. In this case, similarly, this also power domination number is 4. Okay. So this is the case where it is G corona K2, G is K3, and you have taken K2. The other case is P4 corona K2 complement. We have illustrated that the upper bound is achieved. So some more results on the bounds. If G is a connected claw-free cubic graph of order n, then I can say that, so some more adjectives are there. It is claw-free, should be basically a cubic graph. Cubic graph means it's a 3 regular graph. Every vertex has 3 neighbors. Claw-free means it doesn't have K13, the star K13 as an induced subgraph. So claw-free cubic graph, its vertex regularity is 3. It's a cubic graph. There is no claw. There is no K13 as an induced subgraph. So if G is such a graph, then it's a paper by Shao and Kang and Gerard Chang in 2006. It says that gamma PG is less than or equal to n by 4 for such a graph, with equality if and only if G belongs to dk, where dk is the connected claw-free cubic graph formed from K disjoint copies of K4 minus C by joining pairwise 2K vertices of degree 2. So I've taken, say, for example, here, this is K4 minus E. This is also another K4 minus E, and this is also K4 minus E. So I take K copies of disjoint copies of K4 minus E. And what am I going to do? I'm going to join pairwise 2K vertices of degree 2. So this and this is joined. Then this and this is also joined. So this is how you get the graph dk. And for that dk, we can prove that its gamma PG is n by 4. Further, if G is an outer planar graph with the diameter 2 or a connected outer planar graph with diameter 3, then gamma PG is equal to 1. Outer planar means I cannot draw the graph with all vertices in one surface, one face. So a graph is outer planar if it can be drawn such that all its vertices is on some face, same face, which you take it to be exterior. And the smallest example of, just like Kuratowski's theorem, the smallest forbidden subgraphs for outer planarity are K4. You know, whatever way you try to draw K4, I cannot put all the vertices of K4 in one face. And another smallest graph which is outer planar, not outer planar, is K23, complete bipartite graph K23. That also, whatever way you try to draw, you cannot put all the vertices in one face. So K4 and K23 or its homeomorphic copy are forbidden for any outer planar graph. So that is one forbidden subgraph characterization for outer planarity. So for outer planar graph with diameter 2 or a two connected outer planar graph with diameter 3, its gamma PG is equal to 1. And for a planar graph of diameter 2, its power domination number is at most 2. Okay. So this is a break step, 1 minute. Can I have a commercial break? Okay. So far, what I did was I started with the notion of a domination number, defined power domination number, and found that power domination number generalizes the notion of power domination generalizes the notion of.
So someone again has raised hand. To those participants, let me tell you that you can ask your questions at the end of the session. Last 15 minutes will be for the discussions. So participants, you can ask your questions at the end of the session. Okay, sir. Carry on.
Okay. Fine. We'll go to generalized power domination and the notion of bondage in power domination. That's all I want to discuss. So, when did we start? At 3 o'clock?
Yes, sir.
Okay, fine. So, formal definition of PGIS is that PGIS of vertices monitored by S at step I. This is what we did to start with. At the 0th level, we consider the closed neighborhood of vertices of S. That means vertices of S and those vertices which are at a distance 1 or are adjacent to this set of vertices is what's called the domination step. That is what's called PG not S. And iteratively, I plus 1, PG I plus 1 S is union of all NGV closed neighborhoods for all those vertices in the ith level of PGI of S, which are neighbors of V but not already included in this PGIS. This is precisely the definition of power domination which we began with. There is at most one vertex which is not already included in the ith step, and also a neighbor of the step in ith step. I'm going to include that also. That is what's called the propagation step. So formal definition for generalized power domination is I'm going to replace I with 1 with K. So domination step is PGK. 0S is the entire closed neighborhood of S, and by propagation step, as long as there are at most K neighbors, which are K vertices which are not already included in the ith step, which are also neighbors of the vertices of at the ith level, I'm going to include that also by propagation step. And you proceed this, and if minimum number of elements in the set S, which fills the entire graph G, is what's called the K power domination number, and the corresponding set is K power dominating set. So formally, a set is S is a K power dominating set if or KPDS if PGK I naught S is VG for some integer I naught. The least cardinality of a KPDS set is what is called the K power domination number, and written as gamma PKG. This is the work of Gerard Chang from Taiwan, along with Andre Rasport and others, Paul Dorbeck, in Discrete Applied Mathematics in 2012. So for example, for K is equal to 0, it is your usual domination. So I need to take E, G, K, and S as the 4 vertices. By domination, I can fill the entire graph G. Therefore, the domination number, that is P, K is equal to 0, is the usual domination. K is equal to 1 is the power domination, and K in general gives the generalized power domination. So for K is equal to K is equal to 0, what I want to tell is that 4 vertices, I say that the domination number is 4, or P0 is 4. That means I need to produce 4 vertices which dominates the entire graph, and that has been done. And the general, one domination, that is power domination, is I can do it with 3 vertices. So usual power dominating set number is 3, which can be seen. So this is the domination step that has been taken care of, and the next level, this gets monitored, and then at the next level, it gets monitored, and the entire graph is done. Okay, so with this 3, so with the vertices E, S, and K, we can power dominate or monitor the entire graph G. Therefore, its usual power domination number is 1. So 2 power domination number, I need to take only 2 vertices, and if you follow the rules of domination and propagation, that is what is happening, and next level it gets filled up. So for K is equal to 2, we can prove that its 2 power domination number is just 2. So if S is a k power dominating set, then it's also a k dashed power dominating set for all larger values of k dashed. Therefore, we can have a chain of increasing chain of parameters. Gamma g, which is gamma p0g, is greater than or equal to gamma p1g. We have proved that, we have seen that power domination number cannot exceed the domination number. So gamma g, which is gamma p0g, is greater than gamma p1g, etc., greater than gamma pk minus 1g, greater than or equal to gamma pkg, etc., etc. What is interesting is that the above inequality of chain of inequality of the various k power dominating numbers cannot be improved in general. Suppose I have a sequence of finite non-increasing sequence of integers. There exists a graph G with gamma pkg, the k power domination number equal to the kth element of the sequence xk for all values of k between 0 and n. I suppose this is clear. What I mean by that the inequality cannot be improved is that whatever sequence of numbers that you are going to give in a non-decreasing way, finite, I am able to fix up a graph G such that its domination number is the first element of the sequence, power domination number is the second element, and third element is the 1 power domination number, 2 power domination number, etc. Okay, so this is the graph as an example. So for the sequence 7, 5, 5, 3, 2, you take a copy of K7, complete graph of order 7, and for all the three vertices, you adjoin this is K2, K2, K13, etc. This is K14, this is K15, and this is K15. If you consider this graph, obviously its domination number is 7. You can see that power domination number is only 5. 1 power domination number is 5. 2 power domination is 3, and 4 power domination is 2. So generalizes power domination number and also usual domination. The k power domination number is finding it is NP complete for quadrant graphs and for bipartite graphs and as linear time algorithms. So there we have a couple of papers on Sierpinski graphs and Norder graphs, which I will come to later. So this is basically the works of Grab, Chang, Dorbeck, Roscoe, and the French mathematicians and Taiwanese mathematicians. And what I have missed at this point of discussion is the power domination of a product graph, which Dr. Sidhu will take up tomorrow. And there are plenty of results on power domination in product graphs. Product graphs is synonymous with, in some sense, with Sandy Clauser, who is going to talk in this workshop. Okay, so Sandy Clauser has done a lot of research on power domination, product graphs, plenty of aspects of product graphs. So he has done, definitely he has touched power domination also in a paper in 2008 that will be discussed in detail tomorrow. G is a connected graph. Some general bounds are there with maximum degree at most k plus 1. Then its power domination number is k power domination number is 1. And G is a connected graph of order n at least k plus 2. Then gamma pk cannot exceed n by k plus 2. If G is a connected k plus 2 regular graph of order n, and if G is not equal to k plus 2, k plus 2, because if you take k plus 2, k plus 2, that's a graph with the k power domination number 2, gamma pk, k plus 2, k plus 2 will be 2. That doesn't satisfy this, except that then gamma pkg is less than or equal to n by k plus 3, and this bound is tight. So for a k plus 2 regular graph of order n, its general power domination number cannot exceed n by k plus 3. In this context, there is a conjecture which is still completely not solved. So for k greater than or equal to 1 and r greater than or equal to 3, and G not equal to k plus 2, k plus 2, that is an exceptional graph, is a connected R regular graph of order n, then the conjecture says is that the kth power domination number cannot exceed n by r plus 1. That is the result. And for k greater than or equal to r minus 1, we have seen that gamma pkg is equal to 1, which is less than or equal to n by r plus 1. And for k is equal to r minus 2 or r is equal to k plus 2, The previous theorem says that the conjecture holds for k is equal to r minus 2. Yet to settle for k less than or equal to r minus 3. And in a recent paper of 2020 by Lu and Mao and Wang, they have partly disproved this conjecture for regular claw-free graphs. That is the latest result on this conjecture. So we'll end up with one more notion and stop. What's called the bondage. What is happening for the bondage number of power domination? Power bondage number, that's what I meant. Okay, so as usual in the case of bondage numbers, we can define the k power bondage number of a non-empty graph G as a minimum number of edges whose removal from G increases its k power bondage number, sorry, k power domination number increases the k power domination number. So sorry for the mix-up, I shall repeat. So k power bondage number of a non-empty graph G is the minimum number of edges whose removal from G has a general k power k domination number, generalized k power domination number greater than the k power domination number of G. So such a set is B is called a k power bondage set. So clearly BP0 is the usual bondage which I discussed earlier. So this is an illustration. You know, this graph is gamma G is equal to 2. Power domination number is also 2. And in general, gamma pkg you can do with 1. So it is a graph with gamma G2, gamma P1G is equal to 2, and gamma pkg is equal to 2 for all values of k greater than or equal to 2. And BP0G, this bondage number is 2, and BP1, the one bondage number is 2, and k power bondage number is 1 for all k greater than. That you can easily check. We can prove that for all complete graphs, its power bondage number is n minus 1. K power, whenever I mean power bondage number, I mean k power bondage number is n minus 1. And if you take G is equal to complete bipartite graph k plus 2, k plus 2, its bondage number, k power bondage number is 2k plus 3. K power bondage number of Cn is 2, and k power bondage number of Pn is 1. All these are due to Situ Varghese, who is the chair here on discrete maths algorithms and applications in 2016. Was also contained in her PhD thesis, the notion of the k power bondage number of a graph. Some results in general is G is a connected graph with maximum degree at most k plus 1. Then power bondage number is vertex, the edge connectivity of the graph G. And the gamma pkg is equal to 1 in general does not imply that its power domination number is same as the edge connectivity. There are examples, I think it is K3 box, K3 box P2. Let me check 1 minute. The P4 box K2 box is Cartesian product, which will be discussed in detail tomorrow. Its gamma P1 is of P4 box K2. Cartesian product of part of 4 points with the K2 is 1, whereas its edge connectivity is 2, and it is not equal to the power bondage number of P4 box K2, which is equal to 1. So gamma pkj is equal to 1 doesn't mean that the bondage number, k power bondage, and the edge connectivity should coincide. So this is possibly the last slide. Again, the bounds for k power domination number in terms of degree. So BPKG, the k power domination number is less than or equal to minimum of du plus dv minus 1 for all edges uv of G. Degree of u plus degree of v minus 1. And as a corollary, we can prove that for a connected graph G, its k power domination number cannot exceed minimum degree plus maximum degree minus 1. Delta G plus small delta G minus 1. And what is something interesting is that that is the this observation that in general the bondage number and its the values for graphs BG and BPKG, the general bondage number, are not related. That means there are examples of graphs for which the numbers differ. So for a graph G formed from star K1n by subdividing each of its edges exactly twice, its bondage number is 2, which is greater than k power bondage number, which is 1. Whereas if you take k plus 2, its bondage number is k plus 2, which is less than 2k plus 3, which is the bondage number of BPK, generalized bondage number of k plus 2, k plus 2. Also, BP k plus 1 power bondage number of k plus 2, k plus 2 is k plus 2, whereas BPK k minus 1 bondage number is k plus of k plus 2, k plus 2 is equal to 2. So there is absolutely no relations between the values of BD and BPKG. Among the power bondage number of trees, for any edge E in tree, edge E in a tree T, gamma pkt minus C is greater than or equal to gamma pkt. And for a leaf U and its neighbor V in a tree T, gamma pkt minus UV is equal to gamma pkt for only if gamma pkt minus U is less than gamma pkt. And we have a theorem that the power bondage number, generalized k power bondage number, cannot exceed 2 for any tree T, and the bound is sharp, as seen by this following example. We have some more results on k power bondage number of trees. If some vertex of a tree T is adjacent to k plus 2 or more vertices of degree 1, then its k power bondage number is 1. And if T has a vertex V that belongs to every minimum k power dominating set, then its bondage number is k power bondage number is also equal to 1. So these are the references. I will strongly recommend going through. This is the motivation paper, that is first modeling paper 1993. And the paper 10 by Gerard Chang is the generalized power domination of graphs. This is a paper by Sidhu and Dorbet on heredity for generalized power domination. What will happen for edge deletion and vertex deletion and so on, which came in Discrete Mathematics and Theoretical Computer Science 2016. And again, some papers by Dorbet and Henning. Daniela Ferrero from Texas State and Seema Varghese has a paper on some special type of networks like honeycomb networks, which I think Sidhu will discuss tomorrow. Again, classical paper by Fink on the bondage number of a graph. This is a very good book, 23. It's a very good book for those who wanted to do research in product graphs by Hammack, Imrich, and Clausar, Sandy Clausar, 2011. Again, some papers by Hered-Nimi, Haynes, and so on. So we have the two sisters, Seema and Sidhu. Seema Varghese has PhD thesis on power domination problem also on 2011, and Sidhu is exclusively on power domination problem in graphs, 2016 PhD thesis. Again, some papers on power domination of graph products and power domination in some, there's a typo, it is KN, nodal graphs and Hanoi graphs, which is a special type of graphs, along with Andreas Hinz from Germany, which came in Discussion Mathematics Graph Theory in 2018. Okay, that is by Sudeep Stephen, is another person who connects power domination set with the zero forcing number, and so on. So for the last 1.5 years, I conclude every lecture with a social message. We need to break the chain, otherwise we are going to be in trouble. We please keep. And then I would like to congratulate the friend of Cochin University Research Group, Laszlo Lobas, who shared the prestigious Abel Prize 2021 with Avi Widgerson. He came to Cochin University 10 years ago for a conference. Since then, we keep in touch. He's a great mathematician, graph theorist, and belong to the Hungary group led by Paul Erdős and others. So congratulations to Laszlo Lobas for being an Abel laureate, and thank you all.
Okay. The session is open for questions and discussions. Participants, those who have any queries or suggestions can ask the speaker now. So participants, kindly unmute your mic and you can ask the speaker if you have any questions or doubts.
Is Niranjan attending?
Niranjan.
Hello?
Yes, sir.
Yeah. You ask something. Any question is welcome. Or if you found this too high, we will discuss and make it light.
Sir, let me think.
Okay, fine. That's the first step. You have to think.
Okay. Or you may ask your questions in the chat box.
Better
Sir?
unmute and ask. That's the better.
Okay.
Sir?
Okay. Shubha Biju. Please ask.
Uh,
Okay.
Sir, in that's K power domination.
Yeah.
Is power domination is a one power domination?
Yes.
Okay, sir. Thank you.
Because as long as there is only one vertex, which is the neighbor of the vertex already monitored but not yet monitored, I am going to include that vertex also.
Okay,
So
sir.
one domination is usual power domination, and zero domination is our domination.
Okay, sir. Okay, sir. Sir, in this, why we call usual domination as a zero domination?
Now we have generalized this to k power domination. So when k is equal to 0, there is no propagation, it's only domination step is there.
Okay.
So we denote by 0, that's all.
Okay, sir. Thank you. Thank you.
Any more questions from the audience?
I think it will be better to conduct a small test after each session. Okay, so what I said in the morning, I want to repeat. It's a serious affair because the organizers have spent a lot of energy to bring people from different parts of the world. So it has to be taken seriously by all the participants. You have to take home something from any of the lectures.
Any more questions?
Sir, can I ask a question?
Okay. Yes. Yes.
Yes,
No.
yes.
How would you characterize the power domination of suppose, say, a grid graph? Because a lot of electrical power grids are modeled that way, right? So suppose like some n into m grid graph or something like that.
Yeah, that is what's called a graph product. And results on this graph product and grid graphs will be discussed by Dr. Sidhu tomorrow. The entire product graphs.
Okay, sir.
Yeah, we can calculate the power domination number of some standard grids, like PM box, PN, KN box, KN, like that. It comes under the theory of product graphs.
Okay, sir.
Yeah, tomorrow we will discuss.
Okay, sir.
Yes. Naresh Kumar. You can ask now. Naresh Kumar. Any others? So I think no more questions from the participants. Yes, Lijo Vincent.
No, ma'am, if no more
You can ask. No,
questions.
yes.
Hello.
You can ask.
Shall I start? for the vote of thanks if there is no more question.
Yes. Any more questions from participants? No.
Thanks.
Sir, shall we wind up then? Sir,
Yeah.
Vijayama, sir?
Yes, yes.
Okay.
Yeah, we can
Okay,
discuss
okay.
tomorrow
So-
also. Then
Okay, so namaste to all and okay, sir.
Yes, you
Hello,
are
ma'am.
audible.
Is it audible, ma'am?
Yes.
Okay, fine. Thank you. So namaste to all and very good evening to one and all. Let me take this opportunity to thank
Maya, your voice is breaking.
very respected person, Dr. Ampad Vijay Kumar, Emirate Professor, Cochin University. So it's my privilege to have here asked to propose a vote of thanks to Professor Ampad Vijay. Okay, ma'am, now is it okay?
Yes. Some network
Hello?
issues there. Your voice was breaking in between. Yes, you go ahead.
Okay, now?
Maya, you can go ahead.
Yes, ma'am.
Yes.
Yes. Okay. So it's my privilege to have here asked to propose a vote of thanks on this occasion. So I, on behalf of the committee, organizing committee and Department of Mathematics, let me call it as a fraternity of mathematics, together and on my own behalf, I extend a very hearty thank you to Professor Ampad Vijay Kumar for gracing his important works and his thought-provoking section, today's section, actually set a perfect platform for students like us. And also thank you so much for sharing your findings and opinion today based on today's topics, that is generalized power domination. Thank you, sir. We are all inspired by your inspiring presentation. Thank you very much, sir. Thank you all. Stay safe. Okay, thank you, sir.
okay. Shall we close?
Yes, sir. So you can stop presenting now. You are presenting currently.
Thank you all for being here. Do remember to log into next session on time. Next session will be at 11 a.m. tomorrow. Thank you.